Okay, now that we have seen the different types of compounds that can form, we're going to take a look at how we can name compounds. And being able to name a compound is really important because it's important for scientists to be able to communicate with one another about specific compounds. And if we're using a different language, it's going to be tough for us to communicate. So we've kind of adopted this universal language for naming compounds. Now, the first thing we need to recognize is that there's one big division in the way that we name compounds. And that division is between two types of compound. The first one is classified as being organic. Second is inorganic. Now, the difference between the two is, well, it's kind of a tenuous difference between the two of them. There's a little bit of ambiguity, but what we can say in general is that organic compounds are compounds that contain carbon and hydrogen, and typically some will contain oxygen or hydrogen. I'm sorry, not hydrogen, we already got hydrogen. Nitrogen, I guess I could have just used that, and or sulfur. Okay, and typically an organic compound is going to have lots of carbons, lots of hydrogens. So for example, earlier I had introduced glucose, which is C6H12O6. Okay, so that's the sort of thing that you would see for an organic compound. And we're not going to worry about naming those right now. In fact, there's an entire course dedicated to organic chemistry where you will learn how to name those types of things. Now, the reason why we call it organic is because those compounds that have those elements just have a tendency to show up in a lot of living systems. Okay, now, inorganic compounds is going to be virtually everything else. Okay, so pretty much all the rest. Okay. Now, within that realm of inorganic chemistry, there are two different types of compound. The first one is the ionic compound. And the other is the molecular compound. Okay, now how do we distinguish between the two of these? Well, the ionic compound is going to be composed of a metal, so something from the left side of the periodic table, plus a nonmetal, something from the right side of the periodic table. Whereas a molecular compound is going to be composed of a nonmetal combined with a nonmetal. Now, these two different types of compounds are going to have two different naming systems for reasons that I think will become clear once we start naming some stuff. What I want to focus on first are the ionic compounds. And to do that, one of the first things I want to kind of rehash here is the typical charges of elements. Okay, remember there are some elements that take on common charges and some that are capable of taking on all sorts of charges. Okay, so let's talk about the ones that we can predict fairly easily. Okay, and it's all based on group number. Okay, so everything in group 1 takes on a positive 1 charge. So that's things like sodium or lithium or potassium and so on. Group 2 will take on a plus 2 charge. So that's going to be things like calcium or magnesium. Now, we're going to skip all the way over to group 13. Okay, and group 13 takes on a plus 3 charge. So that would be something like aluminum. boron. And then we have group 14. Okay, group 14 is a little bit complicated because it's situated in a way that it could take a +4 or -4 charge, but we see this in things like carbon, okay, or silicon. Group 15 is going to be a -3 charge, so things like nitrogen or phosphorus. Group 16 is a -2 charge, so oxygen or sulfur. Group 17 takes on a -1 charge, so that's all the halogens like fluoride or chloride, bromide, etc. And then group 18, of course, is the noble gases, and we know that they do not take on any charge at all. Now, in addition to these, there are a couple of elements that show up kind of in that middle region of the periodic table that have charges that we can pretty consistently predict. And those would be things like cadmium, mercury, zinc, and silver. Okay, and cadmium always takes on a +2 charge, zinc's a +2, silver is a +1. Mercury, we're usually talking about the dimercury ion, which is going to be 2+ as well. Okay, and it's expected that you know the charges for all of these elements. Now, what about groups 3 through 12? Well, 12 is pretty much cadmium and zinc and mercury. But groups 3 through 11, at least, are full of all these elements that tend to take on multiple charges. Okay, so things like iron can take on a +2 charge or a +3 charge, or manganese can take on a +2, +4, +5, +7. Okay, it's kind of tricky to predict what those charges are going to be. And I just want you to kind of keep that in the back of your mind as we look at how we name ionic compounds. Okay, the way that we name ionic compounds is fairly straightforward. Okay, there's just a couple steps here. The first step is to name the cation. And the name of the cation is fairly simple because it's just the name of the element. Okay, so if it was sodium, we call it sodium. If it was calcium, we call it calcium. Okay, then the next step is to name the anion. And honestly, in about 90% of cases, we can say that the name of the anion is going to be the first syllable of the element's name. Plus IDE. Okay, so if it's oxygen, then the first syllable is ox, and we add IDE to that, so it becomes oxide. Okay, then right after that, all we have to do is simply list the cation followed by the anion. Okay, so let's look at how that would turn out with a specific example. Okay, so let's say we have Na2O. Okay, the name of the cation, well, it's Na, so that's sodium. Okay, the name of the anion is oxygen, so it's the first syllable, so ox plus IDE is oxide. And that's the name of our compound, sodium oxide. And I do not have to in any way indicate that there are 2 sodiums for every 1 oxygen. That's because it's implied by the name. Because we saw earlier in a previous video that if I were to say that I have a compound called sodium oxide, I could figure out what its chemical form or what its formula is going to be by looking at the charges that the elements take on. And here I can see that I have to have 2 sodiums for every 1 oxygen. Okay, another example would be AlCl3. Okay, the name of the cation is aluminum, so we just put that element's name down. Okay, the name of the anion is chlorine, so we take the first syllable of the name and then add IDE, and we get chloride. Okay, and that's how we do it. That's the way it's named. So I expect you to be able to go forwards and backwards with this process. So in other words, if I were to give you a name like zinc bromide and ask you for the chemical formula, I would expect you to recognize that zinc is our cation, bromine is our anion, that zinc normally takes on a +2 charge, bromine takes on a -1 charge, which means we need to have 2 bromines for every 1 zinc. Okay, so you need to be able to go back and forth between the 2. Now, this method works out great when it comes to compounds that have cations with a fixed charge. So in other words, they can only take on 1 charge. But what do we do if we have a transition metal? Okay, so when the cation is a transition metal, okay, we have a slightly different process that we have to go through, but it's still the same basic principle. Okay, so to give you an example of when this is important, let's consider 2 compounds that iron forms. Okay, iron forms FeCl2 and FeCl3. Okay, they look like they're similar, but they're 2 different compounds with different properties. And unfortunately, under the system that I just introduced to you, both of these would have the name iron chloride. But we can't have 2 different compounds with different properties having the same name. That's just dangerous. So we have to come up with a different way of indicating what form of iron, or how do we know how many chlorines are there for each iron atom. And here's how we do that. Okay, we start off by naming it like we normally would. Okay, which would involve calling them both iron chloride. Okay, now the difference between the 2 is going to show up in parentheses between the 2, the names of the cations and the anions. Okay, and what we do is we look at the charge on chlorine, which is -1. Okay, and that's true in both cases. Okay, now the first compound, FeCl2, has 2 chlorines, each with a -1 charge. Okay, so in order for that to happen and still produce a neutral compound, iron has to balance that out. Okay, so chlorine is providing 2 times -1 charge for a total of -2. Iron needs to be +2. Now, over in the case of FeCl3, we have 3 chlorides, each providing a -1 charge. So the iron has to have a 3+ charge to balance them out. Okay, so what we do to differentiate between the 2 of these in the name is to write those charges in Roman numerals. So we have iron 2 chloride and iron 3 chloride. Now, there's an old way of doing this that I just want to kind of mention, but I don't expect you to use this old method. But there were a system of Latin names that were used for the name of the metals. And the Latin names were given suffixes to imply what the charge on that metal was. So, for example, iron 2 chloride would be the same thing as ferrous chloride. Whereas iron 3 chloride would be ferric chloride. Okay, I just wanted to show you that just in case it shows up on your homework or in the textbook or something like that. Now, one more thing that we have to consider here is that there are some ions that are not monatomic. For example, chloride would be a monatomic ion. It contains only a chlorine atom. But there are some that have more than one atom, and we have plenty of what we call polyatomic ions. Okay, and they are exactly what they sound like. They are groups of atoms that have a charge overall. So, for example, we can have an OH with a negative charge, and we call this a hydroxy group. Call it a hydroxy group, but we call it hydroxide. Okay, or we could have something like SO4 2 minus, which would be sulfate, or NO3 minus, which is nitrate, or PO4 3 minus, which is phosphate. Okay, and if you look at table 2.3 in your textbook, has several of these that you can look up. Okay, but these get treated exactly like the monatomic ions. It's just different words that we use. Okay, so for example, if I had a compound that was composed of, let's say calcium and hydroxide. Okay, so calcium has that +2 charge, and we said hydroxide is -1, which means that we need to have 2 hydroxides for every 1 calcium. Okay, now it's very important to recognize the way that we write this out, because if I have calcium with hydroxide and I just put a 2 next to it, there's no way for me to know that that 2 actually applies to the OH and not just to the H. Okay, so we can't do that. Okay, and we can't do this because, again, it doesn't tell us whether or not there's actually an OH group there or not. So the way that we deal with this is that we put parentheses in. Okay, so that's how we would indicate calcium hydroxide. Okay, and just like we saw before, naming these things is a simple matter of naming the cation, which is calcium, and naming the anion. Now here we don't have to worry about taking the first syllable or anything like that because it already has that IDE at the end. So this is calcium hydroxide, like I said before. Okay, what if I asked you to come up with a chemical formula for aluminum nitrate. Well, we'd have to recognize that there's going to be aluminum, which is going to have a +3 charge, and there's going to be nitrate, which has a -1 charge. So the compound that would form would require that we have 3 nitrates for every 1 aluminum. Okay, and this would also apply to compounds that contain transition metals. So, for example, if I had, let's see, nickel 2 sulfate. Okay, we have nickel, and we're told explicitly here that nickel has a +2 charge. Okay, and sulfate is SO4, and it has a -2 charge. Okay, so the compound that would form would be NiSO4. And that's all we would have to do. Okay, we could also go in the other direction. So if I gave you the chemical formula let's see, NO3. Okay, you would need to be able to come up with a name for this. Okay, so we have copper and we have nitrate. And we need to know what the charge on copper is because it's one of the transition metals. Well, we know that nitrate is -1. There's 2 of them, so to balance that out, copper must be +2. So this becomes copper 2 nitrate. Okay, or using the old naming convention, this would have been called cupric nitrate. Again, I'm not expecting you to use this system though.